the lesson of today. And so the last time I told you that we are able to measure the compounds by using these radio telescopes mainly. But also we had some gifts from the nature. So some meteorites, sometimes it fall down on the earth. So we are able to analyze, even if maybe material is burned, but sometimes you can even find something useful. So during the course, you will often hear about the Murchison meteorite. That is a meteorite that fallen down in Australia. And it's a strange kind of, so maybe a rare kind of a meteorite that is based on carbon. And so not only on silicates and so rocks. And so this carbon material contained a lot of compounds like amino acids, other derivatives, sugars, a lot of compounds. But always when an object reaches the Earth, you don't know exactly, you cannot be sure if you had some transformation during the entry into the atmosphere, that it's so after the burning, for example, or maybe if you have some contamination. So it's always difficult to determine. You can use some techniques like the isotopic ratio to understand if you get some contamination, or maybe you use some to determine some amino acids that are not present in the currently organism. But you know that it's quite difficult at the end. So that's why, starting from some years ago, you have some space missions, so some probes that were built to collect samples coming from comets or other meteorites. And so this sample return is the idea of this new era of the study of life. But you know, this procedure are always complicated. They also, it's not possible to make like a radio controlled because I don't know if you are following, but you know, in these days there is a famous probe on Mars that is called Perseverance, and but you cannot radio control because it's too far, and with the light speed, Mars is quite far because it's maybe, I don't know now, but it's 100 million kilometers. So if you try to control, you have a delay that cannot give you the possibility to move this in the correct way. So you cannot drive like in a car. So you have to use the artificial intelligence, you have to make some programmation, you have to make some calculation. It's always difficult like this to do this. But nowadays, so I will make you to see one video. If I'm able. So one video that is related to a space mission that is ongoing. And it's a mission from the NASA. This mission is called OSIRIS-REx. And the idea of this mission is to go on one meteorite that is present in the solar system, so maybe not too far. So the idea is to go there, collect a sample. And why they are interested in this body? Because this body is made mainly in carbon. So maybe we are able to get a sample of this carbonaceous chondrite before the modification that you can have in the atmosphere. So, but I will show you the movie because if you listen, it's quite interesting because you will get a lot of information from scientists and engineers from the NASA.
There are many important reasons for studying asteroids, like the
Sorry, I stopped. Are you able to hear the voice of the speaker or not?
target of OSIRIS-REx, asteroid Bennu.
Yes.
First,
Yes, Prof.
Okay, thank you. So I will go on. So this is the name of the mission. Now the speaker will tell you something more about the mission.
and foremost, for me especially, they're geologic remnants from the dawn of our solar system. They're literally the first material that formed around our star, and they represent the building blocks of planets and we hope, in the case of Bennu, of life and the reason that Earth may be a habitable planet in the form of delivering water and other important volatile material.
When we look at asteroids, which are these primitive objects, these little leftover pieces from solar system formation, and we find they may have organics, then that tells us perhaps the conditions for life could have erupted anywhere in the solar system and Earth was just right.
When we study meteorites, we think they represent these asteroids and their different histories, but they've all interacted with the Earth's atmosphere, its biosphere, its hydrosphere. And so we don't know what effect just interacting with the Earth has had on these meteorites. We really want to get samples that are pristine, and so we can do all of those things through this mission.
OSIRIS-REx is a mission in the NASA New Frontiers program. Our objective is to travel out to a near-Earth asteroid named Bennu, survey that object in great detail to understand its geology, its mineralogy and composition, ultimately select a single location on the asteroid surface to acquire a sample and return that material back to the Earth for scientific analysis.
Asteroid Bennu is a fragment of the early solar system, an unmelted, unaltered piece of the origin of the solar system, and preserved the ingredients, the raw materials that went into the formation of planets, the formation of life. By bringing a sample back to the Earth, such as OSIRIS-REx will do with samples of Bennu in 2023, we'll be able to look at the samples in laboratories around the world to understand in great detail the nature of the sample and its place in the origin of the solar system.
The OSIRIS-REx spacecraft launched in 2016, and it's actually taken us 2 years to get to the asteroid Bennu. And in that time, we had an Earth flyby. So we used an Earth flyby in 2017 to change the plane of our orbit to match Bennu's orbit plane. And it's also provided a great opportunity from a flight dynamics perspective to really calibrate our models and learn how to fly the spacecraft, which will help us in the really challenging part of the mission, which is orbiting in the low gravity environment of the asteroid. Over the past few months, the flight dynamics team has been getting images of the asteroid Bennu, and it started out as just a very small point source in the camera, and it's been getting bigger and bigger and bigger in the field of view. And that's allowed us to perform optical navigation to refine our prediction of the asteroid's orbit and allow us to more precisely navigate and target our approach to the asteroid.
As OSIRIS-REx approaches the asteroid, we've done a series of braking maneuvers called asteroid approach maneuvers to slow down the spacecraft so that we can get into orbit around the asteroid later this year. We're also taking lots of images of Bennu to understand its rotation, look for natural satellites, and potential dust plumes.
This is an extremely exciting time on OSIRIS-REx as we're just poised at arrival at Bennu. And one of the most exciting things to us, and relieving too to the engineers, is how closely the asteroid has resembled what we had predicted. Early on, our science team, prior to launch, had come up with a model of what they thought the asteroid would look like based purely on ground-based radar observations from Arecibo. And from that, they created a reference asteroid that we used as the requirements to design the mission against. But no one could be sure that the asteroid would really look like the scientists had predicted. So it's been a tremendous relief to us to find that the actual Bennu is very similar to what the scientists had predicted. So the science team really nailed it.
Well, right now, as we're approaching asteroid Bennu, we're looking for debris or other objects that are orbiting the asteroid, just in case we need to avoid those. And then once we arrive on December 3rd, we'll perform preliminary survey. And in preliminary survey, we fly over the North Pole, South Pole, and the middle of the asteroid. This helps us to map the gravity of the asteroid and understand how to operate near such a small body. Additionally, this will be the first time that we get close-up pictures of the surface, and we'll know how smooth or rocky the surface that we're going to study is.
As we get closer to asteroid Bennu, we'll begin to map its surface in higher detail. What we'll be able to do is first identify the distribution of rocks and particles that might pose a hazard to the sampling mechanism on the spacecraft. And we'll also get a better sense of what the shape of Bennu is like at smaller scales. Looking at Bennu in more and more detail is going to help us identify all the areas that we shouldn't go to grab a sample from.
Throughout 2019, we'll be doing global characterization of the asteroid, basically making maps of the entire surface. We're interested in its topography. Are there craters? Where are the boulders, the valleys, the mountains of the asteroid? And then we want to understand the distribution of geologic materials. Are we finding different patches of minerals in one location versus another? And why are certain areas have a composition and others may be different? We're going to be looking most importantly for areas where we can collect a sample.
OSIRIS-REx will collect a sample from Bennu using our TAG-SAM, which is the Touch and Go Sample Acquisition Mechanism. What that is an arm connected to this sampler head that you see here. This is similar in size to an air filter from a car. How this mechanism works is there's compressed gas that is released that will stir up the regolith from Bennu, store it into this canister, which we will then put inside of our sample release capsule and bring back to Earth. We will collect the sample of Bennu in 2020 and return it to Earth in 2023.
Once we're in the vicinity of our home world, about 4.5 hours before impacting the top of the atmosphere, the spacecraft spins up and releases that sample return capsule. The spacecraft fires its engines to perform a deflection burn, going off into orbit around the sun, and the return capsule enters the Earth's atmosphere, targeting a landing in the Utah desert. I'll be there on site when we open that capsule up and we see those samples for the first time, and science begins at that point on the next phase of the mission, the sample analysis period.
Okay, I hope that you like the watching. So as I'm trying to show you is that so programming a mission like this is very difficult. You see, you have thousands of engineers and scientists. They have some idea. They try to make some model. And then maybe something is not exactly on what you're looking for or what you imagine. And also, I will show you because later, after this, I have, yes, some question from Johnny. Tell me.
Hi, sorry, Professor. I just might have missed it. How big is the asteroid?
How?
How big is the asteroid? I might have missed it.
Oh, this is not written. I think some kilometers in the diameter. So,
okay. Thank you.
And then I will, so that video was made before the taking sample. The taking sample occurs last year. And now I will show you the video because NASA released the exact video of these taking samples. And if you remember, you have like arm, one arm should touch one part. So it's so difficult because they have to avoid stones. If not, you break everything. You are not able to get back. So they analyze the asteroid in detail, trying to find some sand size. And then you get maybe something that is not expected. And you will see now. So this is the video. This is actually not a reproduction, it's exactly the video. So they appear. So what maybe they never expected is the asteroid is so soft because the gravity on the asteroid is not too much because it's just less big than a mountain. And so while touching the surface of the asteroids, a lot of pieces of the scrap exited because I remember they make some pneumatic system. So it blown away a lot of particles. So actually they collected maybe 10 times more than the weight of the sample that they calculated to do. So they have to perform some calculation for the re-entry of the object. So as you can see, so it's never what you expect. But in any case, so these missions are so made by many people, scientists, engineers, and it's a very huge amount of time and science that you have inside this. Okay, do you have some questions? We can go. Okay, so now we'll start with the slides. Okay. Are you able to see?
Yes. Yes.
Okay, let's go on. So we now, so we continue to, so we finish this part or maybe related to more or less physics of the external environment of the Earth. And but I wish to conclude also because not only you have this science, but also you have that biologists wish to study from the other side, because I told you the approach is from all the sides possible. The other possibility is it possible that some microorganisms or some organisms can survive the condition that you have in the space, and yet some indirect result because you know we have the international station that is one orbiting object made by man. So in this International Space Station, you have many scientists making experiments, and they stay also maybe some up to 1 year or more. And what they found, so they were cleaning, just cleaning the outside of this space station because so the cleaning procedure seems that it's a stupid procedure, but in any case, if you are out of the atmosphere and you have an object, you got directly the sun irradiation. So it means that the surface that is exposed to the sun is so hot, and the surface that is exposed to the Earth is cold. So in between, you have the difference of some 100 degrees. So it's better the object to rotate. So you cook this from all the parts, but usually to avoid this, you paint it in the white. So now you understand why most of the missiles, they are pictured in white color, because they reflect the solar light. But if you have some dust, some particles that sticks on the surface, you will have heating. So what they observed, the space station has some source of light, and they find that they have some debris. So they remove this debris and they collect this. And what they found some some remnants of bacteria. So we know on Earth that is bacteria that is able to stay to resist to high radiation dose, and also it's able to stay without water, because so dehydrated, because you are in the vacuum. So imagine this condition: you are completely in the vacuum, you are exposed to UV light because the ozone layer is beyond you, so it's lower. So you got the UV rays, maximum power of sun, even you got some maybe other particles coming from the sun. So the radiation is higher, but nevertheless they found these bacteria that stuck on the surface, and when they wet this, they are able to live again on the Earth. So the idea of panspermia, maybe it is not so wrong. But first of all, how can bacteria goes into the space station? So the idea is quite simple, because you know we have the Earth is covered by water, so by the sea. And if you have bacteria here you have winds. The wind can make some droplets of water to go inside the wind. Then the water will evaporate. You have the sodium chloride. You can have bacteria stuck on the surface. And then with other winds, because in the higher atmosphere, you have winds blowing at a very high speed. So some of these debris can exit from the Earth. So actually, it's known that while the Earth is traveling around the sun, is leaving some like a smell of Earth. So some particles we are releasing, and maybe some part of remnants or like dormant bacteria, like in this case. And so the idea of the panspermia, so that some microorganism is carried out on the Earth, is not so impossible to think. Okay, so after 1 year of exposure, and they know that there wasn't at the beginning, because before sending something to orbit on another planet, you should decontaminate the probe. I don't know if you ever seen some a movie about this. You see that people are wearing some white covering everywhere, like in the clean room. So because you must avoid to contaminate the environments. So especially for the mission on Mars, so you wish to avoid to carry on some bacteria, so you must decontaminate everything before sending it into space. So they found this, and so they were quite surprised. They know that this bacteria is strange bacteria because it has the DNA for sure, but it has a strange mechanism for the repairing of DNA. So not only it has repairing, but the DNA of this bacteria is covered by proteins. When you break this, you have a piece of DNA, but they are able to stay together because you have proteins inside that are keeping the DNA in place. So this is a bacteria that is able to survive to high radiation doses. But sometimes some teeny animals can survive to the exposure of to the space. So I'm speaking about tardigrades. Oh, maybe I haven't a picture here. Okay, I will show it. The tardigrades are small, so they are multicellular. I don't know if it's correct calling animals, so I opted not by you have no biology here. So, but you have these small, like teeny animals that they resemble more or less in between the dinosaur and the insect. They are very small in size, so less than 1 millimeter of length. But it is well known that these animals, they are very resistant. So it means that if you remove the air, you remove the oxygen, you remove the water, they desiccate, but they can stay desiccated. And after putting water again, you will have the surviving again. So they are not damaged when they are into the dry mode. So it's quite, so in any case, they are more or less the most complex organisms that we know that they can survive like this, because the other were bacteria. These are multicellular organisms because they are some millimeters of length. So they are called also water bears. And you can find this on the Earth, maybe everywhere. So in the dirty water, if you have the hydroponic culture, so you have flowers with the water. Here, the water sometimes contains these animals, so they are spread everywhere, and they are very resistant. And so they found that they can survive to some exposure to space. And so what they did, so they organized one mission, because now you can simulate this condition in the space, maybe quite easy on Earth, but it's another case that you send this into space and then get it back. And so the idea was to send a probe on the moon. This probe contains these animals and other maybe seeds, plants, and then you check, so you add water when you are on the moon, and check if they are able to survive by looking them by a microscope. So something of this measurement with the seeds were made by Chinese, that they sent for the first time a rover on the dark side of the moon, and then reaches the south pole of the moon, and they demonstrate that seeds of peas, I think I don't remember, or beans, they're able to grow even in the condition of on the moon. So obviously they need water, they are heated up, so not the condition of the moon. But in any case, it's possible to. So they wish to do the same with these animals, but what happened? Something goes wrong. So instead of landing, you see, it creates a hole on the moon. It means that the probe smashed on the surface of the moon, crashed, And so the the content of this probe exited on the moon. So actually, we don't know up to now if this animal can survive on the moon in the moon condition. But you see, so that people, so the journalists made this title. So the target is the toxic animals on the Earth have crash landed on the moon. As you can see here, the tardigrade conquest the solar system has begun. You see, our concept of space has begun. So this is the title that you have. So we sent, now we know that we sent tardigrades on the moon. So we spread on the surface. This was not the idea to do this, but sometimes something goes wrong. So because you know better than me, you're also scientists, you know when you start, as one of you told at the beginning, you know how to start, but you know how it ends. So few consequences can give you the correct one, but just one error can make you to break everything. Even for the space mission that I showed you, even the small change in the condition can make the condition to everything to fail. So there is there some chat? Yes, exactly. So maybe we started sitting live. Was not the main purpose of this, but okay, could be a possibility. So we'll see if then later when we go again the moon, if we see a lot of these animals on the surface of the moon, okay, we understand that it's possible to have life even on the another planet, another part of the solar system that is not the Earth. And okay, but I will make now one step back because I wish to make a step forward because we started all this discussion. I see some chat. Yes, this idea of many physicists think like this, that maybe someone or something seeded the life on the Earth. So who knows? In any case, we are not here. But I will tell you other stories about the origin of the Earth. The video is also interesting, but in the next presentations, not tonight. But now, so I started everything because we should to speak about the bricks making the molecules. And so we started to speak about the atoms and then the small molecules into the space. Now we step back and because I spoke about the supernova. And nowadays, again, we get a look on which elements we have on the Earth. So the famous table, periodic table of the elements. And you know that, so if you analyze the isotopes, the isotope ratio, and the composition of the Earth, and on another, for example, planet like I don't know, Venus or Mars, they are not exactly the same. So you have a sign that telling you from which part you are collecting the material, because some isotopic ratio is changing, something is changing between the concentration of elements and so on. But on the Earth, so we have, for example, some strange composition because this is the abundance on this axis and logarithmic. But you see this thorium, uranium, they are very, very heavy elements. And also for someone, they are not forming during the explosion of supernova, but they need something more powerful, like the collision between neutron stars, for example. And why I will spend some words with these elements. So uranium and thorium are widespread on the Earth's crust. They are not as dangerous as you think because the half-life of these elements, that is the time that they need to have the half concentration of that nuclei, it's more than billion years. So they are not so radioactive. They are very well known for the atomic bomb and so on. But the strange things that also, wow, on the Earth we will find many strange things. But on the Earth we have a lot of uranium, thorium. Even in the past, they were so abundant that you have some natural nuclear reactor on the Earth. So in some places you have that the fission of uranium and thorium was natural. So it's so strange, but it was like this because the abundance was higher, And so in some condition, because water also can act as reducing the energy of neutrons. And so it's very rare condition, but it happens maybe at least 10 times in the world that some natural nuclear reactors occurs. They know because in some mining these ores in some place of the world, they found that together with uranium, you have all the possible fission products, but they were natural. So that's so strange. So, but in any case, we have one temperature on Earth, then depends from the solar irradiation and depends on the initial temperature of the Earth, because at the beginning you have some temperature, then you have the losing of energy. So one famous scientist made this calculation maybe more than a century ago, and he saw that the temperature of the Earth is higher than what he expected. And at the beginning he didn't know, but now we know that the temperature of the Earth is a little bit higher because inside the Earth you have the composition of these elements that are producing energy. So some natural fission, or you have the presence of radioactive material. So they are hitting the Earth from the inside. So the Earth is a little bit warmer than what we expect for this composition. For example, on Mars, you haven't the presence of so much concentration of uranium thorium. Also because if you imagine, you have the sun here, Venus, Earth, Mars. If you have heavy element, tends to stay in the inner part, because since they are heavier, they are more attracted by the sun. Okay, in any case, I now forget about uranium thorium because they are not directly useful for the life. But so now we think so that we are playing this game, so we think that we are God. And so as a God, we decide to produce life, and you see the abundance, so silicon, oxygen. So why we cannot start the life with the silicon? This is a famous question that many scientists thought. So you use carbon, but you see it's 1,000 times less concentrated with respect to the silicon. So why don't use the silicon? So we know from the chemistry, the problem, you have a problem with the silicon. The problem is the silicon-silicon bond is weak. So it's not like carbon-carbon. It's weak. It means that in some mild condition, you can have the decomposition of this silicon-silicon bond. Obviously, chemists like to play with this. They create a silicon-silicon bond, but you must avoid for sure the oxygen, sometimes water. So not easy to have a silicon-silicon bond. So, but the silicon make a strong bond with the oxygen. So silicon-oxygen bond is amongst one of the highest energy bond that in the covalent bond that we have. But it's making this bond so silicon can for oxygen, then the oxygen connects silicon. So you have tetrahedral structure, basic tetrahedral structure. And so you can have some isolated tetrahedral, or you can have some double. Are you able to see me, to hear me? Able to hear?
Yeah, your connection dropped for a few seconds.
Yes, I noticed because one warning to me. So have you heard about the silicon-oxygen bond?
Just that it's strong.
Okay. The silicon-oxygen bond is strong, so silicon prefers to bond with the oxygen, not with other silicon atoms. And so by binding with the oxygen, you can have a basic structure that is a tetrahedron with silicon in the center and the 4 oxygen into the vertex of this tetrahedron. So the simplest silicate is an isolated tetrahedron, but also you can have other structure that they are much more complex. I just showing you some of these possibilities. Then if you add aluminum, again, you have a lot of compounds like interesting like zeolites that you will see later because they act as a catalyst. But in any case, you see, it's quite high possibilities. And it seems in the shapes, we have a lot of possibility, but we have a problem. All these compounds are solid. So they cannot have so many interaction one to each other. They cannot, you cannot have some modification because you know that the carbon, the chemistry of carbon is rich because you can add some oxygen, you can add some nitrogen, and so on. So you change the structure, but here you have less flexibility. So from both point of view, mechanical flexibility, also chemical flexibility. So these silicates are not maybe the best choice for making the backbones of molecules that are available for the life. And maybe they can add as a catalyst, they can add as a support, as we already seen in the particle formation into the space. So at the beginning, you have some silicon oxygen or aluminum oxygen, and then you grow some organic material on the top of this. And so, you know, here on the Earth, the amount of all the silicon is inside the crust. And so the Earth is made by silicon oxide, but it's not maybe so useful for the life. So we forget about the silicon. So we need, in any case, we have too much oxygen. So the oxygen is the most abundant here. So we have possibility. So some of the oxygen reacts with the silicon. This helps us. Because why we don't want too much oxygen? Because oxygen is quite reactive. If you have carbon plus oxygen, give you carbon dioxide. And so this is maybe the death of a living system. Because it's so stable, the carbon dioxide, that it's difficult to convert back to some interesting material. Now, actually, you can do it with the photosynthesis, so with the photons, but it's so complex how you can think that it arose at the beginning of the life. In any case, so we wish to remove the excess of oxygen. So for sure, silicon helps us because silicon catches the oxygen, put it into the ground, so it stays there forever. Then also we never spoke here because on the Earth, the hydrogen is only bind. You cannot have free hydrogen on the Earth because the gravity of the Earth is not able to keep the hydrogen. So the hydrogen molecule escape from the surface of the Earth and loses into the space. But in any case, the hydrogen is always the most abundant element. As you can see, maybe more than 90% of the universe is made by hydrogen. So if you have hydrogen, you can react with the oxygen, making some water that is an interesting compound. So even though this for us, so it's so important, it has so strange properties, and see, it can be, while it's liquid, it can dissolve a lot of compounds. So for what we know up to now, is that the liquid water is essential for the life. So we have no other clues, but we know that on the Earth you need water, and water is essential, so liquid water. That's why now astronomers and astrophysics, they wish to search other planets that are able far from here, but they wish to have one planet that more or less can have some liquid water, because maybe it could be interesting for the studying of the life or life energies. And also the liquid water, even if it's strange, it's possible to have also in some moons here in the solar system, because we have the moons of Jupiter. So Jupiter is quite far from the sun, and the temperature is very low, but Jupiter is very big. So if you are a moon that is orbiting close to Jupiter, you will have a strong attraction force, and also you have a strong magnetic field. So it transfer energy. So it's possible to have, for some of the moon, is Io is one of these, Europe is one of that. So for that you can have a crust of ice, but sometimes inside they think that there is liquid water, as we have seen with some radars that we put on some probes. So in any case, nowadays we know that we need liquid water. But let's think about how we can approach the origin of life. So the problem is now we are from this side. So the life is very well evolved. We have a lot of animals, we have a lot of plants, bacteria, fungi, algae, all that you want. But they are so complex. So what we can do when science is dealing with complexity is think that to reduce the complexity. But we know this reduction could be dangerous because maybe you reduce it too much and you lose your objectives. But in any case, we have no chances. So if you want to start to think about life, and only your thing is this evolved life, you must reduce. So if you reduce animal, you will have a cell, animal cell. If you reduce plants, you will have a plant cell. They are quite different, and the plant cells can make the conversion of carbon dioxide in useful product. It's called photosynthesis. And so for prebiotics, some prebiotics think that it is too complex. But in any case, we already spoke about the complexity of the cells, because you see in the cells you have some organelles that are, for example, the chloroplast that which you have the photosynthesis, or you have some mitochondria in which you have the production of energy. And someone think that this were some primordial by itself, some primordial living organism. But in any case, still a mitochondria or chloroplast, again, they are too much complex for our study, because inside of them, here, for example, you can find DNA, again, too complex for our idea. So we reduce more, so we need a simpler cell. So we go to some, for example, bacterial cell. And so, again, too much complicated. We need to separate this into some functioning part. And so what we can think, so if we think about the reductionism, and so you can reduce in several ways, but if you are a biologist, maybe you like more the replication. So you think the DNA and the RNA, that are informational polymers, are among the first that you have to think about. And this is from the biologist's point of view. Or you can think about the compartmentalization. So we never speak about this, but if the cell is working, if one organism is working, you see you have several parts of the cell, different parts. So they are separated one to each other. This one is separated from that. So you need some compartmentalization, because imagine that you want to make a reaction of oxidation and you want to make a reduction reaction. But if you mix together oxidation and reductant, they will react with each other. So in order to make oxidation and reduction, maybe you have to have a separate part in which to perform this. So at the end, you need some compartmentalization, even because the cell, so you must keep inside the precious compounds. If not, they will go outside into the water. Maybe they dilute too much. So you need something that concentrates, that keep safely your compound. So for someone, the compartmentalization is more important than the replication, because as we will see later, it's possible to have some vesicles that are able to grow to duplicate. And so nowadays, I'm not speaking about what is life, I think I'm not defining what for me is life, because for these people studying this compartmentalization, so when you think that you have a small vesicle, then it grows, then it divides into two. For this, it is life for them. When you have a RNA that is able to match another part of RNA, for this, maybe you consider that they are alive. But in any case, for physical chemists, maybe they like more the metabolism, because they think about the thermodynamics, because now we are not dealing with thermodynamics, we are not speaking about this, but the living organism, it's like called dissipative structure, because a living organism it has a entropy that is lower with respect to the entropy of the environment internally. And in order to keep disorder, it must create more disorder. If not, it's not thermodynamically stable. So for the thermodynamics, in order to have life, so in order to have something that is well organized, you need to dissipate energy. So you need to have some so-called exothermic reaction. So you cannot have life if you have an endothermic reaction. And so it is you need energy. You need energy. You're throwing away energy. You are throwing a matter because you are alive if a flow of material enters and exits with a higher entropy in order to maintain your low entropy. So you need energy and you need some mass. We can call this food if you want. Or because we have to breathe, we have to eat in order to be alive. So for someone, it's more important than metabolism. So metabolism first. So in any case, we can see that several scientists think replication first, compartmentalization first, metabolism first, then maybe another thing first. Okay, what we know is we don't know anything because up to now, none of these wall theories created something that is more than some results that you can obtain. Maybe you can publish on good papers, but still they are less flexible than what we need. And then what we can see for the origin of life, you need something that is able to make some evolution. So you need something that can do better. So it can increase, can go something do better, reduce more the entropy and so on. So we reduce. Okay, so we have these three topics. We think about all these three. Then I will introduce another one. So you have these three. So what do you think? We reduce again, we go into chemistry. We pass, so we are in between the biology, systems biology. But if you reduce more, you will you will meet chemistry. And so chemistry, you know, we are speaking about peptides that are enzymes. Also, we are thinking about phospholipids for the membranes, actual membranes. For the DNA, RNA, we are speaking about nucleotides. But for a chemist, maybe they are again too complex. We can, so because some of them are polymers like this. They are polymers, so they are made by monomers. So we can imagine the monomers of this. So we think about amino acids, we think about the nucleobases, but it's different. It has also a sugar, also it has a phosphate here. And for phospholipids, there are esters, maybe easier. You need glycerol fatty acids. So these are compounds that chemists maybe are more useful. So it's a better approach for them. But in any case, we saw that we will see. But we know already something that these amino acids and all these compounds can derive from some simple chemicals or a game or some mixture of elements. And so for sure, we have missed the meaning of life in some of this passage, but who knows where. But actually, this was the first approach for the origin of life study, because you have to start from somewhere. So you cannot start from the most complex. And so you start, because the origin of life, I remember the first people speaking of that, maybe there were Schrödinger spoke about this, some Oparin in the 1920, more or less. They didn't know that the DNA has some helical structure. So it's all later. So before the current biology, they were thinking about this. Okay, you have some comment? Hello? I heard some voice, no? Okay, let's go on. And so, but when you think about the metabolism, you have to deal with the complexity of the chemical networks of connecting all these compounds. And if you see these numbers are related to enzymes, so group of protein that make as a catalyst. And these names are compounds. So you in the current metabolism, we know some maybe not million, but 100,000 compounds that are dealing with the metabolism, because nowadays you have a metabolism for all the compounds that you've seen. So the metabolism is complicated, and inside here, for sure, you have some interesting cycling. You have so some if there are some biologists here, they understand that showing the basics of Krebs cycles or other interesting paths that I study into the course of biology. So you see them, if you think about the metabolism, so you have to deal with this. So for sure, maybe passing from the metabolism A to B to C, maybe you reduce the energy, but if you need the cycle of the life, again, you have to revert back. So sometimes you have to grow into energy. So something must give you some energy, some extra energy. Where you get this? Now we know that in the now metabolism, in the current metabolism, this molecule is the ATP, so adenosine triphosphate. And also another important molecule is an NAD. And so these are compounds, this for the energy, and this for the oxidation reduction. So we are at the basics of the chemistry, because if you deal with the metabolism, sometimes you need to increase the energy because your metabolism has higher energy. Sometimes, so going low energy always possible, going higher difficult, so you need some source of energy. So you need, for example, ATP. Sometimes you need oxidation reduction, you need the NAD and the DH. And so these are the compounds, so they are the currently our currency, because you know, many people, many countries in the world, they have their all own currency. But imagine maybe it was this in the past. Maybe in the past you had many possible molecules that are able to transfer energy, that are able to transfer to oxidation reduction. But then maybe after mixing of this argument, they choose the best one. So they choose maybe the credit card. So you know that the skill is priceless, but for everything else, there is MasterCard. So maybe you choose the MasterCard. And this MasterCard is actually our ATP. So the ATP is money that we can use everywhere, independently from the currency. And so maybe this was the choice. And maybe you see this structure is so similar to DNA, RNA. So for this hypothesis that this ATP first, is called ATP first. For this hypothesis, so the metabolism first invented this ATP, then you have some excess of this ATP. This ATP accumulates and then polymerizes. So because this it's activated, it can make some polymerization. So the DNA, RNA were a byproduct of the excess of this. And later they become able to transfer the information of the molecule. So maybe the molecules using the ATP as the exchange money for the energy, maybe they had later a chance more to become more powerful because they are able to translate the information into DNA, RNA. So this is called the ATP first. So it's one of the theories. And so during this course, we will try to maybe not getting in detail for everybody, but showing you maybe the most prominent scientists that they are thinking that that theory is correct. So can I go on? Let's go forward. Okay, so now this is the idea. So from the reductionism, so we break everything and we start from free monomers and oligomers. So this is the way of the chemistry. So we are in the chemistry part of the selection. So this is called maybe prebiotic chemistry, the term that sometimes we use. So prebiotic chemistry. And then you see this word is not by chance. So you have oligomers, free monomers. So every day, so if you are working with, I don't know, plastics, materials, you are full of monomers. But in any case, the knife never arose from this monomers mixture. So you need something to go up. So going up is increase the complexity. So we need some selection. So you have to choose the best one. You have to choose the one that fits better. So in any case, you wish to use the Darwin's rules. So you wish that the winner is the best one, is able to go on and continue this evolution. So don't worry. So we are against the thermodynamics. So this selection is maybe you have many billion of structure. You select the best fit, and then you work only on this one. But from the chemical point of view, it is not so clear how this process could work. So from maybe biological point of view, you have, I don't know, two animals, one food. The quicker animal is able to eat, the other will die. So it's easier from when you are dealing with animals. What we are looking for when you are speaking about chemistry, nobody knows up to now. But in any case, let's imagine that we have this selection. So if you have this selection, you have some field that we can call pre-biology. I don't know how other words to use. So we have some oligomers that are mixture of simple monomers, so not many monomers, and they have some intermediate grade of complexity. It means that because you know this theory, you think that maybe so you have now we have enzymes that they are very complex. Where I'm writing. So you have enzyme, but the part really working on the enzymes, they are just a few proteins, few amino acids, or if you are like a ribonucleotide, you have that part maybe for the active part is only fewer. So maybe for the best choice, for the best enzymes, you need all this structure. But if I take away this part, maybe it's not like active like this, but a little bit better that nobody. So sometimes someone thinks that this could be the way. So you increase a little bit the complexity. You're able to make some what's called protoenzymes. So some catalysts. It depends from your point of view. So if you are a biology, think about the protoenzymes. If you are a chemist, you think about the good catalyst. It's more or less the same. That words are the same at this level. Then maybe you have some so-called probionts, so polymers highly organized, like more similar than the actual one. And finally, you have the domain of the biology in which we are living now, so biopolymers. So we are here. So what we know is, luckily, we cannot go back and see what there was on the Earth. But we know something that the life on the Earth arose in only maybe 1 billion years, not more, maybe less. So it's so strange because it's from the geological point of view, it's not taking too much time. So that's why maybe someone think, okay, maybe you have the correct compounds, then the life dropped from some meteorites, some other part from the who knows. So in any case, we don't know. Even it's difficult to know exactly which was for example, composition of the atmosphere. For sure, there were no oxygen, but what next? What are the compounds? At the end, we don't know exactly. So we are always in the domain of theories and so now from the beginning. So everybody, when you think about the prebiotic chemistry, so you know the famous Miller's experiment, 1953, and this was the result of the theories of Oparin, and so maybe 20 years before of this, or 30 years before of this date, the theories of the reduction in more or less, as I showed to you, that it's possible to create the life from simple compounds. Even in the past, so maybe some centuries ago, people thinking that, for example, worms and flies, they exit from, so they generate from the flesh, but it's not the case. So nowadays we are not trusting this anymore, but the Miller experiment, it's repeatable. So it's the first example of the chemistry showing us something. So it's a simple experiment. So you boil water with some other compounds inside, and then you add another source of energy, you create some plasma. the plasma is useful because the plasma, you decompose mainly the molecules, you create reactive molecules. Maybe if you avoid this part, you can boil down for more time. So the starting meal experiment boiled off this for maybe some months. So maybe without the plasma, by cooking only, maybe you need, I don't know, years, who knows? We never made this experiment. But in any case, the idea is, okay, on the Earth you have lightning, so the plasma, okay, of course. So even the heat of the sun, the water can evaporate. So we should recreate the starting condition. They put some methane, ammonia, water, and hydrogen. So this so-called the reductive material, because nowadays the atmosphere is oxidant because we have oxygen inside. But if you put oxygen inside, you never add anything, because oxygen is so strong in catching carbon. At the end, you have only the formation of carbon dioxide. So the oxygen kills the reactions. You must avoid this. But we know that in the beginning, there were no oxygen on the atmosphere. So this was in perfect time with the theory. So they tried to do this. They boiled off this. And so you can see this is the paper. So that when I take this. And so the yields are calculated on 59 millimoles of carbon inserted like methane. And so you see the yield are changing a lot. For sure, simpler compounds forms in a higher amount. For example, formic acid, and that is a form, intermediate form oxidative of carbon in between the methane and the carbon dioxide. And so this is the main product, but nobody is interested in this. Also glycolic acid, so maybe remember this name, but up to now they neglected this. It's a lactic acid. We'll see later this could be important, but it was neglected because they were searching amino acids. And they found there's actually some amino acids that they are maybe not properly, they most easy to find, but you can find some amino acid. They found some other form. Then we were in 1953. So this experiment was repeated later and later and later. So with the better techniques, because at that time they just make some paper chromatography to understand what was inside, some distillation. So some techniques that later they changed. So they, at the end, by changing a little bit the mixture, by changing a little bit the condition, you can have other compounds, and then for sure you analyze in the better way. And okay, so since so we are speaking about chemistry today, I will show you some prebiotic chemistry. So that's here. So this is the hypothesis of Miller. So you have this compound, so hydrocyanuric acid, because it's known that it's formed in the sparks. So sparks of methane and ammonia creates this compound, and we know that it's correct because we saw this into the interstellar medium. It's a compound that can be randomly produced by high energy deposited of simple carbon and nitrogen material. So this possibly the formation of this is quite reactive with the carbonyls, so it produces some compound that can be transformed into amino acids. So the alpha amino acid, because we know we need this alpha amino acid to producing the proteins. For example, this is a way from formaldehyde and ammonia hydrocyanide. It's possible if you mix this in lab, you will obtain the glycine after the hydrolysis of the final compound. Or okay, you see, you can obtain also hydroxy acid in a similar way, and so on and so on and so on. Okay, but I will show you. Maybe we never spoke, but other line of idea is nowadays we know on the bottom of oceans you could have some like springs of hot water. They are called hydrothermal water. The water could be very high because they are, if you think about the deep sea, every 10 meters you have 1 atmosphere. So imagine to have maybe to a depth of 1,000 meters. So you are under the atmosphere, and the water boiled at temperatures maybe at 300 degrees at this pressure. And so if you have boiling water here, you have water boiling more or less as this temperature. Actually, I'm speaking about actually. So actually we have these hydrothermal vents. So people thinking that life, some of them think that life arose from these hydrothermal vents. So they think they prepare the same mixture more or less of that you have seen before, but you see it contains carbon dioxide. This is quite interesting, and but also they use some sulfides, and you can see they found some deformation of some amino acids. Also, we will see some other things using some sulfur compounds, but usually chemists, they don't like too much sulfur because it creates very bad smelly compounds. They don't want to use sulfur. Then when you go home, the smell of sulfur is not good. Okay, so we have other possibilities. So you see, 1983, we can make the same by using the carbon in some conditions. So carbon ions in ammonia, you can take this. So this maybe could be a glycine synthesis that you can have into the space, more or less. Or we saw already something similar to ISIS, the photochemistry of ISIS. You can produce hexamethylene tetramine and together with amino acids by changing a little bit the conditions. I showed you the results of Bernstein and Lamandola. Here you see the results of Greenberg. So by changing the soup, the mix, you can have different compounds. All these compounds are of the prebiotic interest because you can find this interstellar medium. We found this, we know that we have. Okay, then we made like just showing you a recent study that we made. So because the idea is, are the natural amino acids the most stable among the isomers? So why we are seeing that the proteinogenic amino acids are alpha amino acids, and when you mix something, you obtain alpha amino acids. So why you can have many ideas. Maybe they are thermodynamically stable or kinetically stable because you have a lot of reaction. Maybe they are not thermodynamically stable, but they are produced kinetically. So the speed of the decomposition is less than the speed of production. Or maybe we have because we have a metabolism producing this, or a combination of the both. Because how we can exclude one to each other? Maybe they are all true or no. Who knows? But here's what we know. We know that nowadays the life start from carbon dioxide, water, and with the photons, you can make the photosynthesis, you can produce everything. So at the end, you create an energy gap. And so imagine that if the amino acids are at this level of energy, see the energy here, you have a less increase of energy, but if the amino acids are there, maybe you produce more energy. So this gap is all free energy that you get. So more this is stabilized, more energy you will get. But maybe if you are too much stabilized, they are so simple, so they are useless. But in any case, you need to stabilize. So we are thinking maybe they are thermodynamically stable. That's why they form in all the possible conditions. So what we done, so we start from isomers of these amino acids, because you cannot think about all the combination of all the atoms in all the proportions. So we start from the molecular formula of amino acids, and then with a program that we create of the possible combination of these atoms. We avoid some structure that has no chemically effect. There cannot exist like a cycle like this. So we avoid very strained cycles or compounds that we know that they cannot be stable under the condition. And then, so this computer program just create the connection between atoms, but we wish to calculate the stability. We wish to calculate the delta G of formation. And so we need to make maybe some DFT calculations. So not possible at this level. So we need to transform this into 3D structure with hydrogen also. But this the structure again is messy, so we optimize with some molecular mechanics. Then we go over. At the end, we make some DFT calculation on this. So for sure, we calculate more than 100,000 possible isomer. So we use some supercomputer because for sure you cannot do this at home. But also we prepare a lot of programs and batch scripts because you cannot manipulate by hand this 100,000 we can crazy. So first of all, we take some simple amino acids. We think, okay, is it true that the alpha amino acid, the moiety, is the most stable? So we calculate, you see this number of possible isomers. And then we see something strange because the ranking, that is the position of this amino acid in terms of stability, is amongst the first. What is the absolute position? So this is the real position, but the ranking is like this because sometimes we obtain, this just to show you, we obtain some molecules that they are not stable, because the real stable amino acid is the number 13, if I remember well. And so one hydrogen is missing here because it's cut by the picture, not because it's broken. Okay, you see, this is the third position. You see this one, this is threonine. It's the third position, but if you check manually this, you see, if you are a chemist, you see this is enol compounds, or aminol, or go on another enol. So you at the end remove all the possible structures that are not stable in liquid water. They decompose with the presenol acids. So luckily we found that this is the first. So after elimination of all the unstable hydrolyzable compounds, it ranked the first position. So we repeat this for all the other amino acids, and surprisingly, they were amongst the most stable. And if it's not so, they stay at maybe maximum 6 calorie mole more than the most stable. So not so much different. I will show you the case of tryptophan. So tryptophan is aromatic compounds. So it means that the ratio in between carbon and hydrogen, so you have less hydrogen. And so you have some more possibility to have structure. In fact, we calculate almost 100,000 structure, and it stays actually at the 30th position. So it's quite impressive, this result, because we are not sure about the non-isomers, but at this level, among all the possible isomers, the actual amino acids are, yes, we can say that they are amongst the most stable of these compounds. Okay, I don't know, now we have time. Do you have questions? Do you have questions? So let's introduce some sugars. Then I will stop. So we saw the prebiotic synthesis of amino acids. Now we move on sugars. And so we step back of some centuries ago. So we jump to 1861 because this guy, so this Russian guy, so it was an important chemist that introduced the formaldehyde. So it was one of the first studying the formaldehyde. Even Butler made another important reaction, is that the formaldehyde plus ammonia makes the hexamethylene tetramine. So this is a discovery of him some year before of this one. So Butler took the formaldehyde. At that time, I don't know that it was so toxic. And he put some calcium hydroxide. He heat up a little bit. Then he tasted the mixture. It was sweet. So this is a reaction easy to make in the lab. And this reaction actually is the production of sugars. So this is so simple. So at that time, it was not interested in prebiotic chemistry or origin of life. But
sorry, Professor.
Yeah, sure.
Was the formaldehyde plus NH3, is that HMT?
Yes. If you make a formaldehyde plus ammonia, you produce the hexamethylene tetramine.
And what is it, sorry?
Hexamethylene tetramine is a compound like this. I'm not able to draw this. Okay. It's like adamantane, but you have nitrogen at the top. So we spoke about the hexamethylene tetramine in some other maybe slides, because this we found interstellar in the photochemistry of interstellar ices, and then it could be the precursor of amino acids also. Okay, so but this was a discovery of Butlerov. Now we are speaking about this discovery. So if you put formaldehyde with calcium hydroxide, you will obtain some sugars. But do you have some question about this?
No, that's okay, actually.
Okay, thank you. So surprisingly easy reaction, and so you made sugars. How it's possible? It starts from a slow reaction. So the formation of this is quite slow. Starting from this is called glyceraldehyde. Starting from this, the reaction proceeds faster. And what you'll see with this reaction, that you can create many of sugar. In the case, you create all the possible isomers because you see there are no serogenic control of this reaction. For sure, not in the previous, so in its reaction. Later, someone tried to make some stereochemical control, but here it's all random. So we are just speaking about, so this you find the name fructose sorbose, but I remember to you that maybe I'm not speaking exactly about these sugars, but I'm speaking about C5, C6 sugars, and they could be ketos or aldose. So we use the name commonly for this sugar, but you have all the possible combinations, so no stereochemical control. So starting from maybe you can call this C2 sugar, I don't know, this is C3 sugar. But in any case, you can produce some Psi5 and Psi6 sugar. And then maybe something more complex, because the reaction does not stop here. So the reaction goes on, and after the production of sugars, you will produce something more complex that up to now it's difficult to analyze. And then after this reaction, the sugar were demolished. Here you can see some, for one modern approach of this, you can see you are also producing some C7 and C8 sugars. Then you see, imagine this, all the possibility, all the combinations. So this is a reaction network, and you can analyze this actually with the current techniques, but you are thinking that if you think that is a message, you're right, because after this formation of this CH sugar, then it starts some reaction that it breaks down the sugar. It produces some other compounds. It produces some yellowish compounds of unknown molecular structure. The most could be some compounds containing a lot of unsaturations, but we don't know exactly, maybe a polymer. And then the sugars will decompose into the acids and alcohols, because you are in the alkaline condition and you have the competition between this reaction and the Cannizzaro reaction. So imagine for each of these products, you can have the oxidation and then the reduction. Then you understand the complexity of this reaction. So this reaction, so we liked a lot because this reaction is autocatalytic. What it means? So when once you form the first molecule of glycerolaldehyde, after some reaction, you have some the formation of this compound, and then you have a retroaldol reaction, giving two molecules of this. So we start with one molecule of glyceraldehyde, it produces two molecules of glyceraldehyde. Then from two molecules, we produce four molecules, and so on, so on, so on. So this is autocatalytic reaction. It means it has an exponential growth into the amount of this glyceraldehyde, but you are eating the formaldehyde. So at some time, you will finish the formaldehyde, and the reaction will start the composition of everything. But since I never told you what is for me life, from the chemical point of view, I can imagine that the autocatalytic reaction is a live reaction. So you can think that, for example, the formaldehyde is the food, and this together with all this compound that closing the cycle, the autocatalytic cycle, this is your living organism. Okay, so you imagine that this is your living organism, and this is the food. So at the beginning, you have only formaldehyde. So you can think that it's non-living. Then you can start with the glyceraldehyde. And this in the cycle, all these compounds, you consider that they are living. Then you have the concentration of formaldehyde drops. You have no more food, so you will have the death of the compound. So if we think in this way, so it's simplistic way, a reduction point of view, think all the possible ways. But in any case, here in the test tube, we are for the first time seeing a transition in between the non-living and the living organism, no? Because if you reason in this way, we made the transition. So this is a living system. If I feed this with formaldehyde, it continues to grow. So if I'm, instead of working in the batch reaction, if I work in the flow reaction, I continue adding formaldehyde, I'm keeping this alive. Once the formaldehyde drops, you will have the dead, so the decomposition of these compounds. So it's easy to perform this reaction in the chemical laboratory. So this graph is obtained by measuring the oxidation reduction potential with a combined electrode. So, and it's a platinum electrode combined with silver chloride. Also, you can use a pH electrode. I will show you later why you need this. And so, as you can see, after the addition of formaldehyde, you have the change in oxidation. So why we are using this? So we never invented this. We just saw what our paper in 1970. But it's quite interesting because so simple later you can follow a complex reaction. Because at the beginning you have formaldehyde, then you have sugars. They are less oxidative reductant than the formaldehyde, and then you have other compounds. So you see the ORP starts. Then at the beginning of the autocatalytic reaction, the potential drops. And then here maybe it is not so visible. It reaches a minimum and then increases a little bit. So from this graph, not so visible, trust me that we made other experiment. Then at this point, we make some sample collection. And you put this in the HPLC with the refraction index and the column that is able to separate sugars. And we see what it's already described. So at the beginning, you have C3 sugar, then C4, C5, C6, and so on. Then we made this mass spectrometry of the compounds. You can see this is the Kendrick plot. And in the Kendrick plot, it's easier to see as in the horizon. If you make a horizontal line, you will see the polymer of starting from some compounds and adding formaldehyde molecules. So 1, 2, 3, 4, 6, 7. As you can see, you have some trends, some lines of compounds that contains a higher number of the formaldehyde monomers. Then we made the determination of this, and we see. Oops, sorry, I put it wrongly to these two. But in any case, the sugar. Yeah, because we can see many peaks, but the sugar concentration, or for example, the C5 sugar, they increase the concentration, then they drop the concentration, start the concentration of the sugar. So exactly on what is described into the literature. I think that for today we can stop here. I don't want to annoy you anymore. I hope that you enjoyed this, especially the video that I found at the beginning. So I let open for the discussion.
Yes, looking at the last, I think it's a mass spectrometer graph, this one. Is every single dot a different sampling, or the same sampling has all these compounds in it?
These are Z ratio. So we use some technique in order to determine this. So we use one program that is used for metabolomics. How it works? So for each MZ, the program will check if you have something like a chromatogram, so increase and a decrease of the peak. If it looks like a chromatogram, for him is a dot, okay? If not, if imagine the peak appears and disappears randomly, for him is just noise. So even you have to insert threshold and so on. And then we made this ratio, so we divide the ratio for the molecular mass of formaldehyde by itself, that it's the monomer. So in this is a method that is used to analyze the polymers. Because for one polymer, imagine you start with the initiator A or the initiator B, and then you attach monomers. So in this way, if you make this plot, putting M here, you will see A here, B maybe in this part. And the first point is the starting MZ ratio of your starting monomer. So here we have different, we have many points also because this technique is liquid mass spectrum. So you have the product plus hydrogen plus sodium, you see many possibilities. So you have to check. So it's possible that one compound have more than one dot, because maybe for one peak is with a H plus, the other peak is with a sodium plus. So we made a lot of analysis for this. I'm telling you simply, but we spent some time to this.
Okay, thanks. So they get more complicated as you go to the right.
Yeah. Okay. Yes. So here we make some evidence, maybe the possible formation of some polymers having a quite high molecular weight with respect to the one described here. But as you can see, here you have also coloration with the related to concentration. And you see these blue dots, they are not so concentrated. The higher concentration are the colored dots here. And they correspond more or less to what is known in the literature. Okay. So today I spoke more about the chemistry. So next time I will start to speak maybe of some nucleotides, some nucleobases, and so maybe in between chemistry and biology.
Are we going to look at autocatalysis more in the future? Because I think it's kind of important for this process.
Yes, exactly. Yes, you're right. Also, if you search in literature, you find some autocatalytic reaction related to life. So many scientists designed some model that are able to perform the autocatalysis. Even some models containing some part of proteins or ribonucleic acids. But so these examples are not so flexible. So what I mean? So this reaction is simple, but it has a lot of compounds inside. The reaction made by design, they are more simpler with respect to this one, and so sometimes they could lack from the possibility of an evolution. Because for the theory of chemical networks, in order to have evolution, you have to change, so you have to possess some network, because one network or reaction, it has more information with respect to the easier reaction. So usually chemists wish to make a reaction having only one transition state, but this is not the correct approach for the origin of life, because in order to study one living system, it's better to have a complex reaction network, because in the network by itself, there is also another kind of information that is inside. So for example, imagine that your reaction catches this compound, so the network will react to produce again this compound because they are all in equilibrium. So it's like a sort of evolution. But if you have a reaction that from A goes to B and from B goes to C, if you kill this, C, you will never see the C anymore. Okay, but if you have a complex reaction network, you delete this, maybe you come from the other side.